Hello, LastCon. Good afternoon. My name is Amiran Alavidze. Nobody can pronounce that, as you might imagine, so a lot of people call me Airman, which is fair. Today, I'm going to talk about securing managed Kubernetes clusters. So when I say managed, what do you guys think about? Exactly. This talk was originally created as an internal talk at Testop, the company I was working for at the time. We were getting ready to launch a SaaS application, a new SaaS application that was going to be hosted in Kubernetes. And this is essentially the result of several months of learning, threat modeling, and incrementally improving security of our Kubernetes environments. And hopefully you'll learn something that you can benefit from later on. Having said that, I'm not here on behalf of my employer, so all of the opinions I present are my own. Before we begin, I'd like to do a really quick poll. Raise your hand if this is your first LastCon. It is for me. Very nice. Who here is out of town? Some people? Perfect. Who is working with Kubernetes today, currently? Excellent. Who just saw Kubernetes in the schedule and thought, well, I should join the cool kids? Perfect. One honest person. Okay, let's get started. And I'll begin with just talking about what Kubernetes is and how it works in general. Kubernetes is open source container orchestration platform that originated at Google. It basically was designed from the ground up to be a loosely coupled a collection of components that enable us to deploy, manage, and scale workloads, containerized workloads. And it's got good support for declarative deployments and immutable components and all those modern kind of things. I'll begin with just a little bit of terminology so we know what we're talking about. Although Kubernetes is container orchestration platform, the smallest deployable workload in Kubernetes is not a container. It's something called pod. And a pod can be one or it can be multiple containers that essentially are deployed together and work together and run on the same host in the same environment. Why do we need pods? Why can't we just go with containers? So oftentimes, as an example of a use case for these pods, oftentimes you will have sidecar containers that do auxiliary work in addition to the main workload that you're deploying. So that would be things like collecting logs and sending them to some log management systems and things like that. The containers in the pods, they're created from images. Image is essentially a template for the container. So it contains all the the binaries, the application itself, all the dependencies, everything that that particular workload or the application needs to run on a host. Now, those pods and containers, they often require configuration information. And so that is injected through objects that are called config maps and secrets. There's not a lot of difference between config maps and secrets. With secrets, secrets are encrypted at rest in Kubernetes, and they're not displayed in plain text. But apart from that, they're fairly similar in a sense that they can be injected in the same ways into the pods and just used very similarly. Then we have deployments. Deployments is a thing that helps us manage scale. So if you usually run workloads not as a kind of single instance, because that's prone to availability issues and whatnot, and deployments is the thing that manages that scale. So you can create a deployment and say, I need 5 instances of this pod, and it's going to be the deployment that sees that you've got 5 instances running. If one of them crashes or terminates for whatever reason, it will restart them and do things like that. And then usually you run workloads so that they're accessible from outside of the cluster, because this is services that your application is providing, either to end users or, like in case of API, to other services. And so you have an object called service in Kubernetes, and this is essentially the plumbing, the networking plumbing that enables people and clients from outside to connect to your workloads that run within the cluster. The last piece that I'll mention that's quite important is namespace. Namespace is a logical kind of grouping of workloads, of things, of resources within the cluster. And as a side note as well, all of the Kubernetes control plane components also usually run within the cluster in a namespace called kube system. So if you want to see like what's this Kubernetes is about in terms of like what things it runs to maintain the control plane, you can check the kube system namespace and the things that are running there, and that's what you'll see there. Now let's look at just architecture in general and understand a little bit how Kubernetes works. So we start with, and by the way, this is a picture from just official documentation. There might be an updated one, but we start with the data store. In most cases, Kubernetes clusters use etcd as the data store, and this is a critical component from the perspective of anything that has at least write access to the data store can fully control the cluster, because that's the state of the cluster that basically defines what runs there. Then we've got the kube API server. And kube API server is how things interact with the Kubernetes cluster. So if you want the cluster to provision new deployment or to provision some resources, you'll be talking to the API server and telling it, hey, apply this configuration. And then it's basically a focal point of the Kubernetes control plane. Then we've got the kube controller manager. And this is just control processes that run within the cluster and look at the data store and basically do something with that state that's stored in the etcd database. And we'll see in just a bit how that part works. There's also cloud controller manager, and this is the component that's responsible for interacting with your infrastructure as a service provider if you need resources like load balancers, et cetera, that can be provisioned through the Kubernetes API. And then last part of the control plane is the scheduler. And this is the piece that when you say I want this new pod deployed, this is the piece that basically calculates based on utilization, available memory, and things like that, on which node that particular workload is going to be scheduled and is going to be deployed. On the right-hand side, we've got basically the worker node. So this is the nodes. This is usually VMs where our workloads are going to be run. And each of those nodes will have a kubelet, which is also part of kind of Kubernetes ecosystem. Kubelet is a component that essentially fully controls the node and monitors the health of the workloads and reports them to the kube API server and monitors the health of the nodes and available resources and all that kind of stuff and reports it back to the API server. And there's also kube proxy. Although it's named proxy, it's not actually proxy. It's just a component that manages IP tables. But essentially, it's there to direct the traffic to the right workloads that run on that specific node. Having said all of that, I'd like to give you an idea of how generally Kubernetes works. And I'll do that through a life story of a deployment. So let's say we want to create a new deployment. We want to run this new workload in our cluster. So what we do is we use kubectl, which is a command line utility that allows you to interact with the Kubernetes cluster. And you say, OK, kubectl, create deployment, give it a bunch of parameters, such as like number of replicas, what image to use, et cetera, et cetera. What kubectl does is it's going to connect to the API server and make that API call to say, hey, here's a new configuration that I want to deploy within the cluster. When that happens, all that API server does, it stores that information in the etcd database, and then it returns back. So the time you run kubectl, it's going to return almost immediately as soon as it sends the information to the API server. doesn't wait for any resources to be provisioned. Then if you want to wait and like know when it's all up and running, you need to check the status of the deployment, check the status of those pods, et cetera, later on. So now in that CD database, in that state database, we have this new object called deployment. In the deployment, there's a number of kind of data points that it will contain. So it basically fully describes that deployment. That will include things like name of the deployment, that will include things like number of replicas that we want, so number of instances of that workload that we want as part of that deployment, the image to be used, and things like that. So this is purely exists in the etcd database. Nothing else has happened yet. Now, here comes the controller manager. So that's that process that runs the control loop, and it sees the deployment, but it doesn't see a replica set, which is an object that deployment uses to actually manage the specific number of replicas for the workloads that are part of the deployment. So it's like, okay, replica set is missing, I'm going to create this replica set. So it's going to inherit a lot of the information from the deployment, create this new object. Again, all this happens in the etcd database. And then we've got also a controller manager, but different part of it called replica set controller, that's going to come and say, oh, I've got this replica set. There's no pods created for this replica set yet, so I'm going to create these 3 pods because that's the number of replicas that I was requested to maintain. So those pods, again, will inherit the needed information like the image name and things like that. So controller manager creates the pod objects. As kind of a last step here in the control loop, we'll have the scheduler come in and see all of these new shiny pods that have been scheduled yet to any of the nodes. And it's going to do its magic, apply the algorithm, and basically assign a node to each of those nodes, of those pods, depending on where it wants that specific pod to run. Again, at this stage, nothing happened yet. This is all information, state information in the data store, in the etcd database. But what happens next is now we've got the kubelet that runs on the worker node that will come and check with the API server and find that there's now a pod that's been scheduled on that node that it hasn't started yet. And this is where the magic happens. So it sees that pod object, it's going to create new containers based on that pod specification, and then report back to the Kube API server saying, okay, now it's running, or now it's pulling image, and things like that. So this is where actually the workload is going to be started by the kubelet once it checks with the API server, once all the other control loops have happened, and basically the pod has been scheduled on that node. Now, why am I talking today about managed clusters? All of those things that I've talked about in the architecture, I mentioned they're kind of loosely coupled components. What that means is they're almost like independent projects that kind of work together in a Kubernetes deployment. And they all have a lot of different options in how you can configure them. So if you try to deploy Kubernetes from scratch, you will find that there's a million different ways to do that. And so you'll have to firstly make those million decisions, but secondly also maintain that cluster later on and maintain the high availability of all the components, including things like etcd, which is not a trivial task. So at least if you're just starting from scratch, my big recommendation is don't run your own clusters, just go to a service that can do it for you, and by the virtue of doing that, some of the things that relate to security of the control plane at least are going to be taken care of by that service provider that does that for a living. So if you're just starting out, don't run your own cluster, do managed. Now let's talk a little bit about threat model. So in terms of the attack surface, like where can things happen in this picture? And mainly that's those 3 places. There's the API server that generally needs to be available from somewhere, because this is how you tell cluster to run new workloads and things like that. There's the etcd data store That's a critical component, but generally you wouldn't want that to be available from outside the cluster for that exact reason. And then there's the workloads, and supposedly you'll be running workloads so that they're accessible from the outside. So in terms of like the externally positioned attacker, this is the main path into the whole thing, is I run this web application or API or something, the service that's exposed to the outside. If I'm able to hack into that application, now I end up in a container in the cluster. So based on that, there's when I think about the Kubernetes threat model, I think about attacks on the control plane. So that's basically interacting directly with the API server. I think about compromised applications that are running in the cluster, so workloads basically. I think about compromised user accounts and their credentials. And I think about compromised images, so basically tricking a company or service to run some malicious code that I've created as part of their cluster. And out of those four, the piece that I would be concerned about the most is this second piece, because that's just bound to happen. We're running workloads in the cluster so that they're accessible from outside, and that means that potentially those workloads can be hacked, and this is a way into the cluster. So let's explore that scenario a little bit more. When we're talking about compromised applications, so what can happen if somebody is in one of the containers? So we need to think about three things mainly. One is what network access does that give them, and what are the possibilities for lateral movement within the cluster? Then cluster credentials. What credentials could be exposed through that application? And also we need to think a bit about the container escapes. Networking. Networking in Kubernetes is an interesting thing, partially because networking is not a core capability that Kubernetes provides. There's these things called networking plugins or CNIs, and this is the component that is actually doing the networking. And you can plug in or use different CNIs depending on your needs. At the core of Kubernetes networking model, though, is basically a premise that all of those things, all of the nodes need to be able to talk to each other without any restrictions or like net agents in between, etc. And there's also this thing called network policies, which allows you to natively facilitate traffic filtering within the cluster. But the difficulty there is support for network policies is not required from a CNI. So there are networking plugins that you can use that do not support network policies, that don't allow you to apply any sort of microsegmentation within the cluster. So what can happen in terms of that network access? So we need to think about instance metadata access, so that magical IP address of 169.254.169.254, and possibly credentials and other useful information that the attacker can get through that. We need to think about Kubernetes control plane access and access to the nodes. And this is because the control plane components are running as part of the cluster. So by default, any workload in the cluster can talk to the API server by using Kubernetes internal networking, using the CNI plugins. And then there's lateral movement. So you will supposedly have other workloads running as part of the cluster. So if there's like only internally available APIs that could be useful, or databases and things like that, you can hop on from that compromised workloads on anything else potentially that's running within the cluster. In terms of credentials, interesting thing about Kubernetes is it doesn't have a notion of a user. So user is completely a concept that's completely outside of the realm of Kubernetes. And generally, and when I talk about user, that's essentially like people who manage the cluster and configure it and do things with it. And so generally, you will have an external authentication mechanism that plugs into the cluster and provides that user information. Though you can assign permissions using Kubernetes RBAC, role-based access control, to those user identities. What it does have the concept of, though, is a service account. And a service account is permissions that can be assigned to workloads that run within the cluster. And an important thing to note is that even if you don't do that, Kubernetes will assign a default service account to every pod that's in the cluster. And also, again, by default, that service account credentials, service account tokens, will be mounted within the pod. And this is how the pod or the workload can get access to the credentials and talk to the control plane. Last thing I'll cover is the container escapes, and I don't want to go too deep into here. If you're interested, there's just an amazing talk by Brendan Edwards and Nick Freeman. It's called A Compendium of Container Escapes. Just look it up on the YouTube. It's got a ton of great information, but ultimately, what we're talking about in terms of conceptually the types of escapes, we've got container runtime vulnerabilities. This happens, so runtime might have an issue that allows a process within a container to kind of escape the container. Outdated kernel, so kernel bugs that some of them are exploitable from within the containers, and as kernel bugs, they allow to kind of elevate privileges and get access to the host itself. There's some misconfigurations that might allow container escapes, so those would be things like mapping Docker sockets into containers, mounting file paths from the host into container that can contain host some sensitive files and things like that. And there's this concept of privileged containers. So privileged containers are created so that that container, that workload, if it needs access to the host itself, this is how you do this. And privileged containers they're not essentially contained. So they can have access to like hosts, process namespace, and networking, and all of that. So now, having talked about all of those beautiful things, and I should apologize because there's supposed to be a demo here, but I chickened out. So instead of a demo, I've got a whole bunch of slides to kind of illustrate some of the points that I was talking about. And so imagine we'll basically start with in a container. So again, it's that scenario where a workload is compromised. So we start with a shell in a container. How do we know it's a container? So the easiest way probably to do is do a process list. And if you don't see a whole bunch of processes, including the init process, which starts the whole system in Linux, that's a good indication it's something containerized. How do we know we're in Kubernetes? So if we check the environment variables, there's going to be environment variables that Kubernetes injects so that the workloads know where to talk to the control plane. And so if you grep for Kubernetes, you will see a bunch of those. So this is a good indication we're in Kubernetes. So remember that networking access, first one was access to the instance metadata. This is an example of that. So we just do curl, whatever you want to check in there. Again, by default, you're going to have access. And that metadata can contain sensitive information. And it's not just information that's kind of like the roles that are assigned to that EC2 instance as an example, but there's also some bootstrapping credentials that the node itself uses to join the cluster as part of the provisioning. So next thing I want to check is that service account tokens. What services are running in my cluster? So I do kubectl get service. We see there's an interesting service called Kubernetes dashboard that's running in the cluster. So we want to see if we have access to it and just do curl. By the way, that kind of weird DNS name, this is how you can access services within the cluster. So it's basically a name of the service dot name of the namespace, and you don't need to know any IP addresses, you don't need to know anything. This is kind of internal Kubernetes DNS service that's handling all of those resolutions. So it looks like from this workload we can access to the Kubernetes dashboard, which is another service running in the same cluster. So it's that network-based lateral movement. And now what what we're going to do is we're going to grab that service account token. Remember the one that I said that it's mounted by default to all of the pods in the cluster. So we're grabbing that service account token. We're going to use it later on, and we're going to do basically a tunnel that will allow us to connect to that Kubernetes dashboard from outside the cluster. So we've created the tunnel. Now we can access that Kubernetes dashboard. We're going to use that token that I just grabbed from the service account to log in, and we can explore what's basically in the cluster. Now what I'm going to show is, so that web shell that we were in, that's the deployment that created that web shell. And it turns out this specific service account has added access to that deployment. So what we're going to do, and this is kind of to illustrate why those privileged containers pose a risk. We're going to make this pod, this container that we're in, a privileged container, and we're also going to give it access to host process namespace. So once we added this deployment, what's actually going to happen, the deployment will say, okay, it's all different now, so I'm going to kill the old one, and I'm going to restart the pod with these new parameters. So we go back to the shell, and this is the difference that we see based on that privileged and the host process ID flag. So now we see all the processes on the host. But in terms of networking, we're still in the container. This is kind of containers network namespace, so I don't see a lot of IP addresses. The IP address that I see here is going to be that pod's IP address where that workload is running. This is just to illustrate kind of what escaping that container is going to give us. We're going to try to access this secret from the cluster called super secret, and we cannot. So the workload, initial workload that we've compromised itself, cannot access that secret. But what we're going to do next is we're going to escape that container using that privileged flag and using the host process ID. So it's we're going to use utility called nsenter that allows you to basically enter some other process namespace. And now once we've done that, we're actually on the node. So that command prompt at the end, that's basically us no longer in the container, but on the node that's running that container. Now, another interesting thing here is that when I said kubelet talks to API server, and it does it, by the way, all the time, to like report state, check for new pods that it needs to start, and things like that. It has to use credentials to connect to the API server. To talk to the API server, you need credentials. And those credentials obviously are on the node. So now that we've escaped the container, we have access to the node, we're going to grab those credentials, kubelet's credentials, and all I'm doing here is trying to access that same secret, but now using kubelet's credentials. And I'm able to do that because supposedly that secret is used somewhere on that node. So the node needs to have access to the secret to be able to inject it into the workloads that it runs. And so now, using these new credentials that I had access to, I can see the secret. As I said, secrets are not displayed in plain text, but what does this look like? It's not actually encrypted, it's just encoded. So all you need to do is base64 decode it, and we got access to the message. This is just another check. Now that we're on the host, we can check also the network namespace and see all of the IP addresses that host has access to. A lot of it's going to be Kubernetes related for like internal plumbing between all the different components and the pods, et cetera, et cetera. So it's not all the IP addresses that basically are assigned to the node, and a lot of them are going to be internal IP addresses that are not accessible from the outside. We can also list all the containers on that node. So Kubernetes used to use Docker as their container runtime. They've switched to containerd not that long ago. So we're just using the containerd command line tool, CTR, to check what other containers are running. This is just purely for demonstration purposes. So now seeing that, so it kind of demonstrates the lateral movement, the container escapes, and kind of the use of credentials that are scattered around the cluster to have access to kind of escalate your access within the cluster. So now let's fix some things. And I'll kind of talk about a couple things here that we're going to fix. One is we're going to create that network policy, a very simple network policy that will block access to the Kubernetes dashboard. So as I said, network policy, it's a built-in Kubernetes concept. The CNI has to support it. And the warning there is that if you apply network policy and CNI doesn't support network policy, it's not going to be applied, but you're not going to get any error messages or warnings or anything like that. So if you're not sure if your CNI supports network policies, it's always best to check. So we're creating simple network policy. We're going to apply it to the namespace called Kubernetes dashboard and to application that's labeled with Kubernetes dashboard. That's the dashboard. And so all we're going to do is we're going to tell it that it's only going to be accessible from within the namespace and not going to be accessible from other namespaces. Once we apply that policy, we can see that using curl, we can check if we can still connect to the dashboard, and we cannot. This is basically a test that that policy worked. The second thing we're going to fix is mounting those service accounts tokens within that pod. So we're going to check that they're mounted. So I do ls/run. We see there's a folder called secrets there. What I'm going to do is, again, edit the same deployment that I've edited before through Kubernetes dashboard, but now just from the command line. And I'm going to add that auto-mount service account token parameter and set it to false. And this is the piece that will stop that token mounting. So after that, again, the pod is going to restart. But after it's restarted, I can see that I do ls/run again, and that secrets folder is no longer mounted, and I can no longer use kubectl because there's no credentials for it to use to connect to the API server. All right, with that virtual demo out of the way, let's talk about how do we just holistically approach securing Kubernetes clusters. And we start with network policies. So I've showed that example of a network policy. That's a native way to basically do microsegmentation or any sort of segmentation within the cluster. When I said that by default, network the namespaces are just logical grouping of resources, by default, no traffic is restricted between the namespaces. So if that's something you want to do, you're going to use network policies to basically enforce that kind of traffic policy. Network policies are not supported by default CNI providers in AKS, EKS, or GKE. So you need to deploy a new kind of networking plugin to be able to use them. But it's a very common way, again, to provide that kind of functionality. Even if you have a networking plugin that supports network policies, by default, no restrictions are going to be put in place. But when you do configure network policies, you can apply them to ingress and egress traffic. So you can allow pods to connect out, or you can block those connections, and you can specify which pods can connect to which other pods, or you can block those connections. And generally, you would use rules based on labels. So you will have pods and deployments labeled. So that's basically another way to kind of logically group things together. So you might have, for example, a web service that connects to a database, and the web service will have a label of front end, and the database will have a label of database. And you can say anything with the label of front end can connect to anything with the label of database, but nothing else will be able to connect to the database. So that's the use of labels. Because the environment is so dynamic, labels are used in a lot of cases for basically identifying things within the cluster. Now let's talk about the credentials. So we've got the instance metadata thing. So with instance metadata, a lot of times there's going to be credentials contained in there. You can restrict access, or you should restrict access to those, either using network policies, or there's also cloud providers support a native way to basically assign permissions to the IaaS environment, to the infrastructure, to the workloads if you need to do that. So for example, if you've got a container that does backups and you need to be able to upload those backups to S3, there is a native way that all of the major cloud providers, Amazon, Google, and Microsoft, basically allow you to assign cloud permissions to the specific workloads that you run in the cluster. Amazon calls it IAM roles for service accounts. Google calls it GKE workload identity, and Microsoft calls it AKS Azure ID pod identity. But you basically can say, okay, here's my role. I assign this role to this specific workload, not to the whole cluster or not to the node that's part of the cluster. And so if you use that, highly recommend doing that. If you don't need your workloads or workloads that don't need access to the cloud resources, you can just block access to the instance metadata altogether using network policies. We've talked about service count and mounting those tokens. My guess is majority of your workloads do not need access to the Kubernetes control plane. They do not need to interact with the cluster. They're just running within the cluster. And so for most of them, you would want to set that auto-mount service count token parameter to false so that you don't, even though there might not be a lot of permissions associated with that service count, but you might just completely remove that access altogether. And the last thing you would want to think about is, how do I manage users? So we said that there's going to be some sort of external identity provider, usually through the same cloud service provider. So it's going to be either Azure AD or AWS IAM and whatnot. So, but credentials, if the users need protection as well. So traditional things like MFA and not like having credentials or not checking credentials into the version control system are still going to apply. Next is the control plane itself. So we've kind of said that there's, as part of that attack surface, we've got the API server, the control plane. By default, all three of the major cloud service providers allow public access to that API server when you provision a cluster. It's probably a good idea to restrict that access to only either networks or like IP addresses that need it. Because even though you might not be exposing the credentials, it's kind of a defense in depth idea that even if I've leaked credentials, if nobody can connect to my API server, I'm still protected. And then as part of the kind of securing control plane, it's also important to keep Kubernetes itself up to date. There's CVEs that are published in Kubernetes components from time to time. And so that's kind of that, just general health and maintenance of the API plane that also needs to happen. I want to mention that GKE has this feature of basically doing all of those updates automatically for you. You don't even need to worry about it. You just say, okay, this is how I want the updates, like just update to the next minor version, and it's going to take care of everything for you. You don't need to be too concerned. Securing the workloads. In terms of the workloads, there's several parameters that you can set on the pod to make the workloads more secure. And those are generally done through that security context. So it's a property on the pod that you can apply. And you would want to look at things like requiring non-root user to run the workload. So that's like what user ID is used within the container to actually run the application. Disallowing privileged pods, so that privileged flag that we had, you can actually set in the security context that this pod cannot be a privileged pod. Disable privilege escalation, so that basically breaking all the set UID type binaries to basically get root access within the container. Disable host file system mounting, that's generally a bad idea because workloads are dynamic. You don't know where it's gonna, when it's gonna die, where it's gonna be restarted, and so relying on host file system is not a good idea, anyways. And using read-only root file system. All of these can be enforced at a cluster level if you want to, but you have to use external tools in most cases. So there's a new feature called pod security. It defines three different profiles that you can apply on a namespace basis. So basically can say, okay, this namespace will have a baseline profile. And those three profiles are unrestricted, baseline, and restricted. And it basically sets or enforces security context within that namespace to which it applies based on that profile. So it's not very flexible, but it's there out of the box. You can use it, or you can use something like Open Policy Agent Gatekeeper or Kyverno to enforce this security context on a more kind of granular level. And similar to the maintaining the control plane, it's also important to keep your operating system and kernel up to date, because that's one of the ways how container escapes can happen. On that level as well, also highlighting that GKE, even here, they support kind of automatic updates of the node. So in a sense, you can set and forget. I'm going to spin up this cluster. I'll enable automatic updates of the Kubernetes. I'll enable automatic patching of the nodes, and I'm hands-on. I'm going to focus on the workloads. There's a couple more interesting things, developments that have not been widely adopted yet. There's some projects that provide better isolation for the containers. So there's like things that can emulate kernel in userland. So even if you've got the kernel vulnerability, it's not going to allow the container workload to escape and things like that. Some of those slowly are making their way into cloud environments and managed Kubernetes environments. But there's also the image side of things. So the whole premise and the whole important attack scenario that we've been talking about was a compromised workload. So you would want, obviously, to make those workloads harder to compromise. And that includes securing the images that you're using. So using images from trusted sources, using minimal images, using CVE scanning of the images, and things like that. All right, last piece that I want to talk about is cloud-native security solutions. These are tools that have been designed to work with containerized workloads and work with Kubernetes clusters from the ground up. And they can do things like providing configuration checks and highlighting security misconfigurations for you. So think CIS benchmark, but they can do much more checks than just the CIS benchmarks. They can do those image and registry scans. So they can basically scan your images and either generate SBOMs or highlight the CVEs that you have in the images that you're running to help you secure the workloads. They can also monitor the behavior of the containers. This can be done depending on what tool you use, either on a rule base. So think, I've got Apache, all of a sudden it starts a shell and starts running commands. So that kind of scenario. So that's the type of things that the rules allow you to detect. Or some of them do anomaly detection. So they baseline what your workloads generally do, and then if there's anything outside of that established baseline profile, they can alert you about those activities. And that can be in terms of binaries that are executed within container. It can be in terms of network connections that are initiated by the workloads. It can be in terms of even the syscalls that the workload makes. So if all of a sudden it starts trying to mount file systems or do things like that it didn't do before, that's the alert that you'll get. Some of the cloud-native tools can also do traffic monitoring within the cluster. So it's kind of an overlay over the CNI, and they can act as an internal WAF within the cluster or just enforce kind of additional capabilities to enforce network policies on top of just the built-in network policies. And they can provide some information that's useful for forensics analysis. So if you did have an incident they'll provide additional context of what was happening within the pod at the time of the incident and give you that additional signal that you can use for forensics purposes. With that, that's basically all the content I had for today. I've got some recommendation about open source tools you can use. These are freely available. A lot of the companies that make them also make the cloud native security solutions. Trivi is probably one of the best ones. They've expanded the functionality quite a lot lately. It was initially created as the container CVE scanning tool, but now it can also do infrastructure as code analysis. It can do cluster configuration analysis and a whole bunch of other things. Falco is the behavior monitoring tool. So Falco is an open source project. There's a commercial version that's using the same engine, but essentially you can fit it rules to detect those things like, as I mentioned, like Apache service starting a shell and things like that. Kubebench and KubeHunter can assess the configuration of your cluster. Kubebench strictly focuses on CIS benchmark. KubeHunter does additional checks that are not part of the CIS benchmark, and it can also do like cluster assessment from within. You can deploy it as a workload within the cluster, and it can see what workloads that run in your cluster have access to and what other things. Basically, check for that privilege escalation and lateral movement type misconfigurations. KubeSec and Gripe. KubeSec does infrastructure as code scanning, so kind of similar to some of the Trivi functionality, and Gripe is another CVE scanning tool for images that is fairly widely used. Some resources, if you want to learn more, there's an excellent introduction to Kubernetes course on Coursera, on EDX. That's official CNCF. So CNCF is a body that maintains or manages the Kubernetes project. So this is an official intro-level course, but even that provides quite a lot of useful information if you want to just start learning about Kubernetes some more. There's a bunch of labs. Some of them are free. There's Play with Kubernetes, Kube by Example. There's a couple ebooks that Aqua Security and Red Hat have released that talk about securing Kubernetes. There's also OWASP Kubernetes security cheat sheet that's quite useful as well. And Microsoft, not that long ago, they've released kind of a MITRE attack style matrix for Kubernetes-based attacks. So if you're into like mapping and checking different scenarios that can happen and mapping incidents or just threat models to those different scenarios, that's a good resource to check. I've got linked to my slides if you want to check them. This QR code, if it works, leads to the slides as well. So that's basically the same as that link down below. Feel free to check them out, use them as you will. And thanks so much for coming. I'm happy if we've got time. I'm happy to, if anybody's got any questions. I would think about this problem from kind of the perspective of data. So if I've got data that's much more sensitive than the rest of the data, this is when I'll start thinking about, should I segment this into a separate cluster, or do I have the tools that are built in Kubernetes, like the network policies? Do I feel like that's enough of a segmentation for, because the big thing, again, we need to be concerned about is that lateral movement. So network-based attacks is probably the biggest part of that. So if I'm confident I'm able to kind of sufficiently segment the services and the data stores, et cetera, within the cluster using the network policies, using RBAC and things like that, that's kind of the deciding factor. But ultimately, it's like within this heap of crown jewels, do I have like the crown jewels of the crown jewels? Is there a subset of data that's so sensitive that I'd rather not even risk like those network policies working well? I'd rather split them out to a completely different cluster. That's how I would think about that. But again, I haven't had much experience with multi-tenancy. When I first found that option, I was very confused. I'm like, why would you build privilege escalation into the system and then allow it to disable it? What that actually talks about is in Linux, you might have a setuid binary. So binary is just that basically, like, I'm running as non-root user, but I can run like ping or traceroute that use some of the syscalls that basically require root access. And so I might have that binary as setuid binary. So when I run that, or like a change password binary, because it modifies the user database, right? So basically what that block privilege escalation, or I forgot the exact name of that feature is, it doesn't allow setuid binary. So even if you run setuid binary within the container, with that turned on the pod or in the container, you're not going to get root access to as part of using that setuid. So it basically blocks setuid binaries. That's the gist of it. It's a fairly simple thing that at least to me, sounded very confusing when I was initially learning about it. All right. If there's no more questions, thank you so much. Hopefully this was useful. And again, feel free to use the slides.